This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
BBC Sounds. Music, radio, podcasts.
You're about to listen to a brand new episode of Curious Cases. Shows are going to be released weekly, wherever you get your podcasts. But if you're in the UK, you can listen to the latest episodes first on BBC Sounds. I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science. Hello, we've got quite a brain-bending question today. Have a listen to this.
Hi, my name is Adam. I'm from Hertfordshire. And my question is it possible to transfer memories between different people so that other people can experience other people's memories?
I mean, that's quite a nice idea, isn't it? Transplanting memories from one person to another.
I mean, is the idea that you could relive a moment that you've envied somebody else having?
Maybe. Moon landing.
Okay, yes, a great historical one, winning an Oscar.
Yeah. One memory I'd love to have, do you remember a couple of years ago at Glastonbury when the rapper Dave got somebody up to rap the Thiago Silva song?
Oh, yeah.
I mean, I think that would be... Just the emotion of that moment would, carry you through for the rest of time, wouldn't it?
Possibly. I mean, we're presuming that the person remembers it vividly at all, or was it a mad blur that they don't remember at all?
Because I think the point about a memory is it's not like you're watching back a videotape, right? It's like, it's very malleable.
Yeah, fuzzy, I think. And that is a problem with it, like whatever. Problem with it, with how far this technology can go. Because I can't even remember things vividly that happened to myself, let alone pass them on.
There are definitely some things where I can remember what I was wearing. I can remember, details about the book that I was reading at the time.
Yeah.
Insane levels of detail. There are some memories that just have that sort of crispness to them.
And yet, what happened yesterday? What did you do yesterday?
Oh, gosh, you know what, actually, I've got to the point now where I've been travelling around so much that when I arrive at the baggage carousel at an airport, I can't remember which city I've just been in. I just be like, right, what country was I in?
Somebody said to me, "Oh, how was your weekend?" I said, "I can't remember what I did," and I had been on the telly. I'd literally done the last leg live on Channel 4. And then 2 days later, I don't know, I don't think I did anything at the weekend. Just, people forget things.
I know, people forget things.
It's a really unreliable thing. But here, my other question with this is, because you don't just want a snapshot, because you've seen a picture of Neil Armstrong on the moon. You want to feel what it would like to be Neil Armstrong. And is that in your memory? Is it like when I remember things, do I get the same surge of adrenaline? Do I get the same surge of oxytocin, whatever, if I think back to the birth of my children, whatever? Do you get the same emotional charge? Because that's what you'd want to live.
I think you would. Imagine if you could have a museum where you go, you see pictures of the moon, whatever, and then at the end you get to sit down and have the memory implanted into your head.
Oh my God, that'd be very good. You'd make a fortune with that.
You would.
Yeah.
You would. Right, let's see if we can start a new business plan over the course of the next half an hour, shall we?
Excellent. Joining us in the studio today, we have Professor Chris French from Goldsmiths University, where he studies anomalistic psychology.
And Amy Milton, who is a Professor of Behavioural Neuroscience at Cambridge University.
Amy, our listener Adam was talking about transferring memories of specific experiences, like somebody receiving an Oscar, say. But there are many kinds of memories, aren't there?
Yeah, absolutely. So there are sort of broadly two categories of memory that we can think about. There's explicit memory, because you have conscious access to the content of those memories. Sometimes it's also called declarative memory as well, because you can declare them to the world. And so that would be memory for events, but it would also be things like semantic memory, which is memory for facts. The other type of memory is implicit memory. That's where you don't have conscious access to the content of that memory. And that would be things like riding a bike. So you learn to do it. You have acquired that. It is a memory. but you can't pass that on in words. So they're also called non-declarative memories. And there's a whole load of different types of memory that would fall under that class.
The sense of, I know who this person is, that's implicit or explicit?
The emotional content of the memory would be an implicit memory. So, the emotional content, and even things like knowing like what cues in your environment mean. So the sound of the ice cream van being a good noise, that's an emotional memory that's completely implicit. You learn it through association, but until someone draws your attention to it, you probably haven't thought about that before.
You know how people say, oh, I've got a good memory? Like, if there are different types of memory, can you have a good memory in a different type of a way? Like, I mean, some people are really good at quizzes, for example, right? I guess that's semantic memory, is it?
Yeah.
And then terrible at remembering events and occasions.
Yeah, absolutely. I mean, if you look at people who have, particular like brain damage or neurological disorders, you can see that these things separate out entirely. So you can have people who have a disorder called semantic dementia, where they gradually lose what objects mean and what they are.
Facts and things
go, but their episodic memory stays okay, whereas for Alzheimer's patients it's the other way around.
So some people forget the capital of France but can remember what it felt like to be a 14-year-old on the swing.
Yeah.
But then in did you say dementia it's the other way around?
In Alzheimer's, it's the other way around. So episodic memory, the memory for events is lost, but they still know how to navigate through environment. They know what keys are, for example, and they know that keys unlock a door.
Oh, how interesting.
Because I'm very bad with faces, very bad with names, but can remember everything that happened on Nights Out, going back all the way. It's grand, to an irritating extent. So some things brilliant on, other things not as good on. And as you get older, presumably you also, some of these skills recede anyway.
Yeah, there's an idea actually that as we get older, we encode or we store episodic memories in a different way so that we become much more reliant on gist. Like if you've had loads of really similar experiences, there's no point in storing every single detail of every single experience. You can just get the gist of it, and then when you recall it later, you'll just fill in the details.
Sorry,
and that makes a difference.
It's just a scientific term.
Gist is a scientific term, yeah. I mean, we can talk about schemas if you would prefer, but gist is basically what it is.
It feels self-fulfilling because gist is the only word that's defined by itself. The gist is the gist of something. Yeah, it's grand. I mean, it's vague both in definition and use. By the way, how accurate are the movies Inside Out and Inside Out in terms of that? Is that genuinely based on anything?
100%. We all have those little characters in that
But there's an element of core memories. There's a lot of things discussed in that, like whatever. Did they make a lot of that up?
I think one of the things that is a shame they didn't quite get in Inside Out, but they're great films. I'm not having a go at Inside Out, but the idea that the memory is stored in like a complete form and the whole experience is kept in that little ball and you can recall it as it happened. That's not how memory works at all. Like it turns out we actually make up a lot of stuff when we're recalling memories. We store like the key things that you need, the gist, and the key details that would be like weird in that experience. But we don't have the whole of that memory stored in one go. Like the example I often use with students is like if you think back to like the first time you ever walked into college, like what shoes were you wearing? Like, no one remembers that unless you were wearing, like, particular fancy shoes. But when you remember it, you don't remember it with no shoes on, right? You just make something plausible up. So we do that with a lot of stuff, and we're just not necessarily aware of it.
There is something interesting in that, actually, because Dara was saying about how he couldn't remember what he did at the weekend, and it turns out that he had appeared live on The Last Leg. And I imagine that for most people in the world, that would be quite a memorable event. But for Dara, I guess, it's actually not that unusual. I mean, the thing what you're saying is like, it's the kind of how weird moments are.
Yeah, how distinctive is this? How much of a sort of shift from my normal experience is this? That's the stuff that's worth remembering.
All right. Well, okay. So Chris, then we introduced you as a professor of anomalistic psychology. What on earth is that?
I thought you might ask that. It's basically seeing if we could come up with psychological explanations for experiences that many people would label as paranormal. It's everything from kind of alien abduction claims to people who think they've got psychic powers or ghostly encounters, past life memories, anything that's weird, we're interested in it. And can we come up with explanations, non-paranormal explanations, and where possible can we actually produce some evidence to support our our explanations for these phenomena.
Okay, if we are just remembering these sparse details then, the gist of it, as it were, does that mean that we can kind of influence each other in the way that we fill in the gaps? I mean, we're talking about transferring memories here. If two or more people have a collective experience, do they sort of influence each other's memory?
Well, they certainly can, yeah, and that's the thing. I mean, if you've got a situation where a group of people have witnessed something unusual, like a crime or a possible sighting of the Loch Ness Monster or a UFO, they're going to discuss it before anybody formally interviews them to collect their account. And if you've got one person there who is very, very confident and gives their account first, but maybe includes some inaccuracies, that can contaminate other people's memories. And this is a definite thing. It's called the memory conformity effect. We've looked at it in an anomalistic context. This was a study where, I'm sure you both remember Uri Geller.
Of course.
I remember when he first appeared, because I used to believe in all this stuff. And one of the things that Geller became famous for was apparently being able to bend metal just by gently rubbing it. I've now got lots of friends who are conjurers, and basically they can do this, and they say, it's a trick. It's sleight of hand. It doesn't involve anything paranormal. And if Uri's doing it using paranormal powers, he's doing it the hard way, because it looks exactly the same when you do it as a trick. But other people came back and said, oh, no, it can't be, because I've seen him do it, and the spoon carried on bending after he'd put it down, so it can't just be sleight of hand. Now, Richard Wiseman, who you may have heard of, he's famous. Richard is a member of the inner magic circle, and he knows all about the power of suggestion. So he did a neat little study where he had one group of volunteers who watched this video of an alleged psychic who was in fact a conjurer using sleight of hand, who, in this case it was a key, bent the key using sleight of hand, puts the key down, there's a nice close-up shot, and you hear him say, it's still bending. You have another group who get exactly the same, but they don't get that suggestion. Of those who get the suggestion, 40% report they think the key carries on bending. It's a really simple manipulation, and virtually nobody in the other group does. So we borrowed that. Richard published his results. We borrowed his video, but we put a memory conformity twist on it, where people watch the video in pairs, and one of the pair was a genuine participant. The other one was a confederate working with us. The idea was you watch this video, you discuss what you've seen, and then you report back to us independently what you've seen. And the confederate was instructed to either say during the discussion, yes, it did carry on bending, or no, it didn't. And that then has an additive effect. So if you're in the condition in our study where you get the suggestion from the psychic and you get the reinforcement from the co-witness, we got to levels of 60% of people reporting they thought the key carried on bending. It absolutely doesn't. So it's not just what happens when you're witnessing an event, it's also what happens afterwards can influence.
We're a mess. That's what I'm getting at. We're a complete mess. Okay, I want to know, Amy, though, when you're experiencing something, when an episodic memory is actually being formed, so let's say you're, Neil Armstrong landing on the moon, for instance, what's actually happening in the brain? Because this is, at the heart of it, this is a physical process that's happening, right?
Yeah, absolutely. So our best theories at the moment suggest that what happens is memory trace form. So you're having that experience that's going to activate lots of different brain regions. And that's going to, if for an episodic memory, that's going to activate this region called the hippocampus, which is kind of tied up to all of these different regions that are getting all that sensory experience. What will happen then is that you'll have cells within the hippocampus that are all becoming activated together, and those cells will then undergo a process that we call consolidation. That basically means that they undergo kind of a structural change in the brain cells themselves that allow them to signal more efficiently to each other if part of that memory trace becomes activated again. So once that consolidation process has happened, that's thought to take somewhere around like 4 to 6 hours to finish. If you then present part of that memory again, you give like a retrieval cue, that should then, because the signalling is now more efficient, that should allow most of that trace to become active again, and that will then be the process of recall.
So then, okay, if this is, as you're describing it, right, you at the cellular level, right, you've actually got something physically changing, then doesn't that mean in theory that you could sort of implant a memory?
Well, that assumes that we're all wired up in exactly the same way, right? Because our brains form through experience. So we're born with way more connections between brain cells than we need. We actually lose a load of those in the first few years of life, the ones that we don't need. So we're not necessarily all wired up in exactly the same way. So the idea that you could take one even if we could image it, which you can't in humans, if you could take that whole memory trace and then put it into somebody else's brain, it wouldn't necessarily give the same sensory experience in that new brain because it's not been wired up in exactly the same way.
Okay, you said there for a second, we can't do that in humans yet.
Yeah, we can't do that in humans.
Right, does that imply?
It has been done in mice.
It has
been done in mice in a very, very selective, specific context. So this is work done by Paul Frankland and Sheena Jocelyn's lab in Toronto. So the way that we perceive smells is really, really predictable. So within the olfactory bulb, in the nose, and mice have massive olfactory bulb, they're very, very kind of based on smell. You can predict how certain odours will activate certain cells within the bulb. So if you present almond odour, for example, you know this one cell is the one that lights up. Actually, it's two, but in any case, you can predict which ones are going to light up. Which means if you can then switch those on and off, you can make the mouse think that it has perceived almonds when actually it hasn't. So what they did was they paired the fake almond odour with either good or bad outcomes. So they were dealing with male mice, so the good outcome was access to a lady mouse, and the bad outcome was an electric shock. And then they put the mice into
What a brutal dichotomy that is, isn't it?
two different groups. You want to be in the lady mouse group.
Yeah.
And then they just put them on, gave them a choice. It's like, do you want to go to the almond odour or do you want to go to this other odour?
So wait, they hadn't smelt.
They'd never
smelt almond.
Yeah.
But you know that in another mouse, when it smells almond, a switch goes on in the brain. So then you get these other mice who've never had the smell, turn the switch on, and then say, which way do you want to go?
Here's a lady mouse. Learn that this smell predicts the lady mouse, or learn that this smell predicts shock. And then when you actually give them the real smell, they will go towards it if they think it means lady mouse, and they will go away from it if they think it means shock.
They remember smelling something they've never smelled.
And they took it one step further as well. So this is like the first fully artificial memory. They also took another group of mice, did the stimulation, so the fake almond odour, stimulating the nose, and then they switched on parts of the brain that are associated with punishment or with reward, and then did the same test. Here's the almond odour. They've never had any real experience of lady mice or shock or anything, but they still went towards the almond odour if they thought, or if it had been paired with rewarding stimulation in the brain, and away from it if it had been paired with punishing.
So in the first one, they remembered a smell that they'd never smelled. And then in the second one, they remembered a smell and an emotion with something they'd never experienced.
Yeah, that's exactly right.
Wow. Okay, I'm going to get my head around that. And also the poor mice. Do they all find time with the lady mouse? At the end,
I don't know.
They brought you a nice farm where there's just lots of lady mice, so they can hang out with the lady mice. I'm also looking around for a lady mouse.
No more lady mice for you.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
So that's an example of a simple artificially implanted memory in a mouse, but it turns out that we humans are all susceptible to having rich, meaningful memories that are actually false. Have a listen to this.
My name's Al Hopwood. I'm an artist, writer and curator. And between 2012 to 2016, I gathered an archive of false and non-believed memories from the public. There's one particular one where someone had a memory of seeing their dad in a play, in like an amateur dramatics play, and they can remember what it felt like. They can remember feeling slightly embarrassed, and there was their dad doing this slightly hammy performance up on stage, and they remember it as having aunts and uncles all around them, kind of like the whole family was in this small theatre where they grew up. And then much, much later, they were at a family gathering and started talking about this amusing recollection, only to be told by their mum that there's no way that that could have happened because they weren't born at the time. And so it was obviously a kind of family anecdote that had been told over and over again and then had been imagined and then somehow lodged as a recollection. And this idea of transferring memories between different people is quite interesting because it kind of happens anyway. There's a really funny one where a brother and sister can remember really vividly their mum trying to resuscitate their pet goldfish with a straw. So it died. It was floating on the top of the tank, which of course isn't funny. Took the goldfish out, and then with a straw was trying to blow air into it to resuscitate it. And then many years later, they were chatting to their cousins about this memory, and they turned and said, "No, that was our mum who did that. That was your aunt, and we have the recollection of our mum having done that to our goldfish." I mean, where the truth lies in that, I've got absolutely no idea. But it's absolutely fascinating. I'm fascinated creatively in what has now really become quite an established cognitive link between memory and imagination, and that a memory is a process of storytelling.
Chris, first, why is our brain not better at stopping this?
Well, it's a byproduct of the way that our brains have evolved, which is basically to kind of be the most efficient in terms of we don't need to take every single detail in. So we remember the important stuff, we remember the gist. But that means, well, that means that sometimes we fill in those gaps unintentionally, unconsciously, with what we think must have happened. But there's also the fact that we can imagine things, okay, very, very vividly. And we know that if you get people to imagine something that didn't happen and imagine it repeatedly, then in some people, especially those with very good imaginations, they can later confuse what they've imagined for something that really did happen.
Can you use this to your advantage? Can you, knowing that people have this like messy memory system, can you like deliberately implant false memories in other people?
You can, yeah. I mean, there's a range of techniques now. It was Elizabeth Loftus who was the kind of queen of false memory research. I'll describe one of her initial studies. Basically, you get people to come in and you say, we're interested in autobiographical memory, so episodic memory for things that actually happened to you. And we've spoken to other family members. They've told us about these things that happened before you were 10 years old. And they give you 4 examples. 3 of them actually really did happen. You really have been in touch with their family to find out. But one of them is made up. In the original study, it was getting lost in a shopping mall at about the age of 5, being very upset, and then eventually being reunited with your parents. Now, people often will obviously say they don't remember that because basically it didn't happen. But you get them to say, go away and think about it and see if any more details come back, and we'll interview you again in a week's time. And then you do that a couple of times. And it varies from study to study, but you'll find that around about 25 to 30% of people that you put through this process will then come up with false memories of this event that didn't happen, sometimes even kind of elaborating on it, introducing extra details that you didn't give them, and so on and so forth. There's all kinds of different scenarios that people have used. I mean, knocking over a punch bowl on the parents of the bride at a wedding reception when you were a kid.
Brutal.
One really kind of interesting study was implanting false memories for having been involved in a serious crime which involved the police, where you were the perpetrator. And people start off saying, no, I don't remember that. By the end of it, I say a sizable minority are saying, yes, I remember that now, it did happen.
These are all quite negative things. I mean, I was just thinking about, can you do the opposite? Can you trick people into being confident, like, self-assured, like capable humans by telling them about something great that happened to them in the past?
I mean, again, in some of Elizabeth Loftus's more recent research, they've convinced people that either during childhood there were certain foods that they hated, or there were certain foods that they loved. And the idea is that potentially this could be used to kind of stop you eating unhealthy stuff and get you to really eat more healthy stuff, which, is a kind of good outcome. But is it justified? Basically, you're playing around with people's pasts. You're kind of convincing them something happened that didn't, And so it raises a whole host of really interesting issues. If you could come up with kind of reliable ways for kind of editing out, really traumatic memories, then, that might be something that's worth doing.
That's something you're involved with, Amy, isn't it? Editing real memories?
Yeah, that's right. So the research that my group's really interested in is understanding the contribution of those emotional memories that we were talking about earlier to mental health disorders. So we're really interested in disorders like addiction and alcoholism. We're interested in post-traumatic stress disorder. And then other groups have also been interested in this as well and looking at other disorders like phobia, for example.
So if you have a fear of dogs because you were bitten by a dog as a child, or you'd mention that always, if you can somehow edit out that memory?
Yeah, that's right. So as Chris was saying earlier, there's this idea that what we've actually evolved is this much more kind of dynamic, flexible memory system. So memories can be updated. You just have to get them in the right conditions to update. If what you expect to happen and what actually happens is not the same, that suggests your memory needs updating, and so we can get the memory back into this mode where it becomes editable. While the memory's in that editable state, normally you would then introduce new information, you would update it, and then it would go through this process where it kind of restabilizes, the memory trace restabilizes in the brain. If you get the memory, though, while it's in that editable state, and you stop that reconsolidation process from happening, which you could do with drugs, you could do with other kind of behavioural manipulations, then you can stop that restorage from happening, and so you should be able to stop that memory being restored in the brain, and therefore stop it from having an impact on behaviour in the long term.
Okay. I want to make. I mean, this is crazy. Like, what you're doing is extraordinary. Okay, so let me make sure I understand this then. So it hadn't quite landed with me when you said earlier memory is about looking forwards, but is what you're saying that the whole point of memory is not so that you can think back wistfully about the nice days that you spent on a bicycle when you were 16. It's all about predicting your environment to keep you safe and sort of prosperous in future.
Exactly. So memory has evolved, we think, for predicting the future, not for looking back at the past.
Wow. Okay, so then this idea of like, okay, a dog bites you and it's horrible and you don't like it, and so therefore you're scared of dogs in future. You're saying now you can take that memory and then, as you're recalling it, change your association with it.
Yeah, that's the idea.
How do you get it into an editable state, as you described?
Yeah, so you have to have a mismatch between what people are expecting and what actually happened. So there's a really nice study that Meryl Kint did at the University of Amsterdam where she was looking at spider phobics. So she was getting people to come into the lab, and she told them that she was going to get them to go and pick up a tarantula sitting at the other end of the room. And, she's bringing them, and she's got videos of this that I've seen, and she's bringing them to the door of the room, and people are really, really panicking because, they do not want to go near this spider. And then she pulls them away from it. So they've geared themselves up. They're going to have to go and handle this tarantula. And then she pulls them away, and then she gives them a pharmacological treatment. So she gives them a drug called propranolol, which is a beta blocker. So
calms your heart down, basically.
Calms your heart down, but also has effects in the brain as well. Then what she did, they have this treatment where, they have this one session where they're told they're going to have to handle the tarantula, and then they get propranolol or placebo, depending on which group they're in. Next day, of course, the placebo group come in, she handled the tarantula, I'm not going near it. The group that had the propranolol not only go up to the cage, not only open the cage, they actually allowed the tarantula to crawl up their arm.
Wow.
And this effect lasted for at least a year. She followed up for at least a year. And they were, in fact, if anything, approaching the spider.
So they didn't need the propranolol?
Again, it was just a one-off.
Oh my gosh, this is so... Okay, so
you basically retrained their brain.
Exactly. You've prevented that fear of spider memory from being there. Really interesting, though. It took them about a year to stop describing themselves as spider phobic. They had to have enough experience of not being afraid of spiders in the real world for that kind of autobiographical semantic memory to update and say, I'm no longer spider phobic. But the fear was gone within a single session.
Can we very quickly ask you the specific question we said, could we transfer memories of specific experiences? Do you think that will happen ever?
Specific experiences, yes. I think very, very unlikely. I mean, I'm always happy to be proved wrong, but I think the idea of being able to take a memory trace from one person and implant it in another just seems really unlikely to me because, brains are different. We all are, and brains evolve across time, right? Like our experiences change who we are as we get older as well. So I just think to take a memory from one set point in time, even for the same brain, and implant it, in another point in time. I think
so. We couldn't even use it on our own memories to.
Unfortunately, I think that seems unlikely.
Okay. So you can't go into the same river twice, as they say. It's changed. It's not the same river.
So
it's not the same brain. Exactly. Yeah.
Oh, do you know the really shocking thing? I've never been on the last leg. Ever. Just imagine.
Nice try. They're still not inviting you again.
Thank you to both of our guests, Amy Milton and Chris French.
So, Dara, do you remember what we just talked about?
Look, there was something about lady mice and how if you want to woo a lady mouse, buy her some almonds. That's really that was my takeaway.
You got the gist of it.
That's it. That's the whole game, isn't it? Yeah. Oh, good. Thank heavens, pressure's off. Subscribe to Curious Cases on BBC Sounds and make sure you've got push notifications turned on, and we'll let you know as soon as new episodes are available.
Hello, Greg Jenner here. I am the host of You're Dead to Me from BBC Radio 4. We are the comedy show that takes history seriously and then laughs at it. And we're back for a brand new series, Series 9, where we're covering all sorts of things, from Aristotle to the legends of King Arthur to the history of coffee to the reign of Catherine of Medici of France. We are looking at the arts and craft movement and the life of Sojourner Truth and how cuneiform writing systems worked in the Bronze Age. Loads of different stuff. It's a fantastic series. It's funny. We get great historians. We get great comedians. So if you want to listen to You're Dead to Me, listen first on BBC Sounds.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
BBC Sounds. Music, radio, podcasts.
I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science.
I have issues with this week's show title.
Tell me.
Well, it just says Invincible Moss Piglets.
Yeah, okay. Go through it word by word for me.
Invincible.
Yeah, agree.
Okay, moss.
Yeah.
Piglets.
Yeah.
Are they all? These are all terms where...
Yeah, what's your problem?
I feel we have to communicate this, both to me and to the people at home.
Okay, we're talking tardigrades.
Okay, yeah, I faintly know about tardigrades.
What do you know about tardigrades?
Well, I didn't know they were invincible moss piglets for a start. I've heard them referred to as water bears. I've heard various nicknames. They get a lot of...
Very difficult to kill.
Okay. Are they piglets?
Yeah. Yeah,
sort of. Are they made of moss?
They live in moss. I think by the end of the half hour, you will be convinced that there is no other title greater.
Okay.
Because the thing is, we've actually had a lot of questions come in to curiouscases@bbc.co.uk about tardigrades. Have a listen to this one.
My name's Vivian Parish, and I live on the Isle of Lewis in the Outer Hebrides. In Star Trek Discovery, they had this massive tardigrade that was shooting the ship around the galaxy on a mycelial network. So I know that's science fiction, but there's things that we can learn from tardigrades. They seem to be able to withstand radiation, and they live through droughts. And how can they actually help us if we do go to space? So can they give us any information to protect ourselves?
Okay, so we're hinting at the invincible there, not so much the moss piglet.
No, that's coming later.
Okay, Vivian also wasn't the only one. A chap called Andrew Love also wrote, and he noted, I often hear the joke that come the apocalypse, the only thing left alive will be cockroaches and Keith Richards. But are there any other organisms that could live after the end times? In particular, what about tardigrades? Just cut to the chase, Andrew. Just ask, what about tardigrades? Don't have to give the big build.
I think it made it much more colourful that it included Keith Richards. And I think, any opportunity to include Keith Richards should be taken.
I'm just saying, if it was like a telegram situation, we had to pay by the word, just what about tardigrades? Would have achieved the same thing.
Here's the thing, though. Today, tardigrades. Next week, we're going to do Keith Richards. An entire episode.
Is half an hour enough to really, at a molecular level, probe what's going on with Keith Richards?
He survived the apocalypse. So this is it. This is what we're doing today. We are seeing whether these little superbugs can genuinely survive an apocalypse. And to do that, we are going to talk to a couple of experts to see what they make of it.
Yes, trapped in the studio with us, we have Dr. James Fleming from Oslo University.
And after searching through the scrublands and remote grassy plains, we have also captured, from the University of Copenhagen, Dr. Nadia Muberg.
Yeah, why is this so Scandinavian, this particular episode? Is there a particular Scandinavian tardigrade obsession?
Well, I think Scandinavians actually love tardigrades, I guess.
You're the go-to people for this. It used to be pillaging, and now it's
upgraded.
Yeah.
Okay, we're going to get to the magical powers that these things have in a moment, but I think it's better that we start off with the basics. So can we describe what tardigrades look like?
So they're tiny creatures, less than a millimeter, has 8 legs, with a mouth opening and anus or cloaca in the other end. So they have most of the organ systems that you would normally see in larger animals. So they have a gut system, they have a brain, they have a ventral nerve cord, they have a lot of muscles, and they have gonads. They're built of around 1,000 cells.
They're quite cute in a lot of ways.
Well, at least some of them are. Some of them look like genuine bears. That's why they have the popular name water bears. But there are also species that are more alien-like, with long sensory organs coming out of the head and different places on their body. So a tardigrade is not just a tardigrade. Well, there is 1,500 species described of them, and we know we have many more that we haven't described or found yet.
And as well as water bears, I mean, people do actually call them moss piglets, don't they?
They do call them moss piglets, and that's because they live in mosses. So there are a lot of species living within the marine environment, within the ocean. We have species living in freshwater ponds, and then we have a lot of species which live in mosses and lichens.
Also, they are a little bit piglety. I mean, they've got like quite round tummies. On the front of their noses, I'm using body parts that they don't have here, but on sort of the front of what you might call their face is almost what looks like a little snout.
So they have something that is called stylets that come out of the mouth regions, which they use to penetrate cells of other animals and plants. And then they have a large suction pharynx, which they use to suck out whatever fluids they can get out of the cells that they penetrated. And then they have a gut system, like other animals have. So there is actually quite a lot of complexity. They're very small, so they are less than a millimeter, but you have quite a lot of complexity within this maybe 500 microns of an animal.
Is that too small to see with the naked eye?
Some of them have very strong colors, and if they do have that, you could see them just barely. But otherwise, you would need a 20 to 30 times of magnification, right, to be able to see them.
Would you just find them in your garden? I mean, are they constrained to certain parts of the world, or do you find them in people's gardens?
So you would find them, for example, on your roof, in the gutters, the roof gutters. You will find them. The thing about tardigrades is that they are actually aquatic animals, and this means that although they have invaded land, they require a film of water surrounded them in order to be active. And that means that if they don't have, even though they are living maybe in your garden, in the moss on your roof, they will only be active and, so to speak, alive if they have this water film around them.
James, the thing that always distracts me about tardigrades is, well, their appearance, obviously, because they look like little mammals. They do look like they have the shape of a little bear with a face. Like they've a body limbs and a face.
Yeah, I mean, that really quite like distinctive kind of lumbering gait that you see whenever you see them under the microscope is part of why they're called water bears, because they do have this very bear-like movement under the microscope.
And they've been around for a long time?
A very long time, yeah. So the first tardigrade fossils date back to the Cambrian, which is 530 million years ago, roughly.
So that's like pre-dinosaurs.
Yeah. That's about 400 million years pre-dinosaurs.
Whoa.
But are they everywhere?
Yeah, pretty much. Yeah. Indeed, one of the most studied tardigrades on the planet was first found in a rain gutter in England.
Do you find them in very cold places?
You do, yeah. So there are a few species that live in Antarctica. Acutonchus antarcticus. It's got a good name.
Stick an us on the end of any word.
It's great.
It's a scam. It's a whole thing. Latin is just a thing to get funding. Did you go looking for?
So that's what I've been doing this afternoon. I was very graciously provided by your producer with some moss from his roof.
I believe he took his life into his own hands.
Yeah, he clambered onto it. Yeah.
I was told stories of a rickety stepladder. Very adventurous. So I've been steadily sieving through that. So really all you need is a bunch of kitchen equipment. If you have a box of the moss that you've collected, you hydrate the moss overnight, so you keep it in some water overnight, and then you get a sieve, you squeeze the moss through the sieve and into a Petri dish, and then look through the Petri dish with your microscope.
Oh, that's really easy.
It's very, very straightforward, yeah?
Yeah.
Did you find any?
I did find one.
Can we see it?
You can see a picture of it. Unfortunately, and this is another chink in the invincibility claim, while trying to transfer it from the Petri dish that was full of moss fluid into something nice so that I could actually show you, it got stuck in the pipette and died.
What?
As Nadia, well, yes.
Apocalypse? No problem. Yeah. Pipettes? More difficult.
Way more fragile than they've been led to believe.
So shearing forces can sometimes be a problem for tardigrades.
Show us the photo of... Yes. Okay, I am looking at a photo taken down a microscope.
Yes.
And it looks... it looks like there's a little sort of really tiny worm at the bottom.
Yes, that's a nematode. Yeah, at the bottom.
Great.
Yep.
Disgusting. And I'll be honest with you. Oh, hang on, is that it there?
Yeah, that's
that little guy.
Yeah, that little guy.
Okay, so you can sort of see you can see a couple of the legs. Oh no, you can see all three legs.
You can see all the legs, and you can also just about make out the little claws as well on the bottom.
Oh, look at that! There he is, little water piggy. Mm. Since passed.
Yeah, no longer with us actually. He's not as joined together as he was during the photograph. Is that his little face there?
That is actually the back pair of legs. The little face is right at the front. Yeah,
okay.
all the way around.
Yeah. Oh my God. Yeah, no, I get the shape of him all right. Yeah. Wow. Congratulations. And then you killed him.
And I killed him. I'm sorry.
Casually murdered the one we found. I mean, we've talked up their ubiquity and their invincibility. Found one, killed it. That's the running total at the moment.
Tell you what doesn't kill them though, drought. Because they are pretty famous, Nadia, for this one incredible ability that they can just survive total drought. How on earth do they do that?
Bottom line is that we don't actually really know. One thing that we do know is that when the water leaves, it's very important for them that they tuck in their cells and they tuck in their organ systems, and they contract into what is called a ton state. And when the water is then gone, then there will be like this very small ton, maybe a volume decrease of 80 or 90% or something like that. When water then comes back, then they will be able to revive
and come back to life.
So they basically stop their metabolism, and this is the way they have adapted to life on land. Is that when they come from water, or life comes from the ocean originally, so did we. But they have adapted to land by simply allowing water to leave their bodies. So they close down all their life's processes, and then they wait. wait until water comes back into the moss cushion or the rain gutter, and then they start living again.
This sounds like a sort of extreme form of hibernation.
It is.
But how long can they survive like this?
So there are good empirical data made in the lab that say 20 years at least. We have some Japanese colleagues that have revived tardigrades from Antarctica after they have been frozen for 30 years. I think there is an anecdotal report from the 40s with a Italian guy that rehydrated some mussels from a museum that were 120 years old, and then he saw a little bit of movement from the tardigrades, but they never came really back to life. So 30 years, we have good empirical data on that. And seen in the perspective of the normal tardigrade life, which is maybe a month or 2 months, then I mean, putting 30 years on top is quite a lot, actually.
But like, if we just curled into a ball, there's a lot more chemically happening here.
Unfortunately, that's not going to work. Chemically, there are quite a lot of theories on what's going on. They actually have a suite of genes that are unique to tardigrade-specific heat-soluble genes that help reinforce the cells against dehydration. Some species of tardigrade have up to 33 unique genes just to deal with drying out that no other animal on Earth seems to have, which is kind of quite a serious investment into this kind of singular strategy. We aren't exactly sure how all of this is working on a protein level, but we're starting to come to some understanding of what's happening. There is one protein that last year we were able to visualize its expression within the cell as the tardigrade was entering the tun state. So we could see where it was appearing as the animal dehydrated. And it looks like they form fibrous struts inside of the cell that seem to prevent the cells from shriveling to a state that would damage the nucleus and all of the important internal cell things. Whereas other proteins form these gels that stick around the scaffold. Almost, you can think of it a bit like a kind of intracellular cork.
So they're built to reorder themselves to a certain extent so that the important bits will remain protected.
One of the things that we have been working with in my group in Copenhagen is actually the muscle systems, and they are built of actin and myosin filaments, which are also what we have. And we see that when the tardigrades, they tuck in their cells and the organs, they use their muscles, and it's very important that they have ATP while doing this. ATP is the energy reserve of the cells. And once the water sort of disappears from or totally evaporates from the tun state, then our hypothesis is that these filaments and the tardigrades are filled with muscles. This is one of the organ systems that are really large compared to their small size. Then the filaments will actually lock in a rigorous state. So the myosin filaments and the actin filaments, they cannot detach when ATP is gone. And this is much like what we see when we die. The rigor mortis state is what happens when myosin is still attached to actin. And this is how they keep their 3D structure while in the cryptobiotic state.
How quickly does this whole process occur? Not just the drying out, but how quickly do they resurrect?
Minutes. I mean, if it's just a sediment from the rain gutter, it will take a few minutes that you can revive them. Maybe 20 minutes, 30 minutes. The longer time they have been in the desiccated state, the longer time it will take them to revive.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
Okay, all right. In terms of apocalypses then, so drought, check. Floods, Check.
Well, they were water-based. Yes, yeah, floods are fine. They're ground floods.
Floods are
yeah.
absolutely fine.
Yeah.
But our listener, Vivian, she was asking about space travel and whether we could learn anything from tardigrades by sending them to space. And you know what? She was on to something.
Hi, I'm Thomas Boothby, and in 2021, I sent tardigrades into space. Our animals were sent in a frozen sort of state of stasis up to the International Space Station. And once they were in space, they were thawed out and they were cultured on the space station for up to 4 generations. And what we really wanted to do was to look at how tardigrade gene expression was changing under those conditions over time. As we leave Earth's atmosphere, which is very protective, you get exposed to much more of this cosmic and solar radiation. You know, one thing that radiation does is it damages our DNA. And so, you know, we expected and we are seeing that the tardigrades upregulate genes involved in repairing broken DNA. They also upregulate genes involved in making sort of prophylactic strategies for this. So they produce things called reactive oxygen species scavengers, which can help sort of ameliorate the effects of radiation before they have time to really do a lot of damage. The idea is that if we can learn about the tricks that tardigrades use to do this, we might be able to develop countermeasures or therapies that would allow humans to have a more productive and long-term presence in space.
Ooh, I say. By the way, that was Thomas Boothby from the University of Wyoming. So, all right, they're resistant to radiation. Tell us a little bit more. How resistant are we talking?
So, one of the ones we found in the rain gutter today, Rhamazottius varianatus, can comfortably survive while active up to 5,000 grays, this is a measurement of radiation per unit weight. Humans can take about 5.
How on earth are they doing this, though?
There seems to be a tendency for tardigrades to upregulate these damage-suppressing proteins that repair the DNA, rather than actually really attempting to resist high amounts of radiation. It's perhaps better to think of it more as healing than it is actually resisting.
Because obviously, when it comes to humans being in space, the dangers in cosmic radiation and the damage it would cause in terms of mutating DNA or cancer risk for long-term space exploration is something that people are very aware of. So can we learn from them?
So very, very recently, there was a Japanese research group that showed that they were able to express tardigrade genes inside cultured human cells.
Oh. Like a fusion.
However, there's something very, very different between doing that in a petri dish and doing that in a person.
I mean, give me the caveats in a minute. I want to know the results first. Were these human cells, when they had been infused with tardigrade DNA, suddenly superhuman?
They were able to survive a higher amount of radiation than regular human cells could. Not quite to tardigrade levels, but yeah, better than the baseline. Better than me.
I mean, there's a lot of upside from 5 to 5,000. There's a lot of space to wiggle there. Yeah. Because tardigrades also have there are at least 2 of the missions in which tardigrades have done exciting work in space. They were put on the outside of a probe once and left floating around for 10 days, unprotectedly, in the freezing cold. Oh yeah, pointedly. They put it out there for 10 days, float around, yeah. And then they tried resurrecting them, and I think it was more than 50% of them or 60% of them returned.
Yes, yeah. So they had just over a 50% survival rate after being exposed directly to the vacuum of space,
which is higher than your pipette.
Yeah, higher than my pipette.
100% death.
Much higher than me when exposed to the vacuum of space.
The tantalizing space trip they made, however, was in 2019. They're in the Bereshit probe, an Israeli probe that crashed onto the moon. And it is thought it had on board a number of tardigrades in the crash, which may have ended up on the surface of the moon.
Yeah, so they sent a mission to the moon. it crashed and it contained a few thousand tardigrades on that mission.
Uh-oh.
As tardigrades can, in theory, survive the vacuum of space, do we now have tardigrades on the moon?
Moon moss piglets.
Moon moss piglets living on the moon moss, like clangers. Unfortunately, or fortunately, unfortunately for all the pure tardigrades in the crash, but fortunate for any concerns about ecological disaster.
Or indigenous moon piglets.
Indigenous moon piglets, yeah. It seems that the tardigrades wouldn't have survived the crash. We found this out because a group at Queen Mary's University in London shot tardigrades in the ton state out of a gun.
Jesus. This is what scientists are doing with your public money, people.
At close to 900 miles per hour, which is quite close to the crash velocity, and found out that even within their super protective ton state, that does not save them, unfortunately.
Not even one? Wow.
I mean, it'd be more poignant if there's one. Just one.
One victor.
One just staring at the earth in a curled up state.
Mummy.
Yeah, wondering why am I the only one who survived?
I mean, how many do you need to launch out the gun at what speed before you get a probability version below 0.05?
Yeah.
I agree.
I want to see the footage of this experiment. I want to see how this is done. The methodology of it all seems insane.
Yeah. If you are concerned about the well-being of these tardigrades, just don't write to us.
So the question is, as originally asked, was could they survive an apocalypse?
I think that it depends what the cause of that apocalypse is. So, as we mentioned before, these potential, at least proto-tardigrades that we found in the Cambrian period 500 million years ago, there have been at least 5 really major mass extinctions since then. Not just the asteroid that destroyed all the dinosaurs, but also grand eruptions of undersea vents that choked almost all of the life out of the ocean. There have been huge turnovers in what life on Earth looks like. And for some reason, tardigrades seem to have done quite well with that. So there's been 5 mass extinctions. They can probably survive a 6th.
There are other types of apocalypse, though, Nadia. What about a nuclear apocalypse?
So they are definitely vulnerable to mechanical stress, as James showed you guys, but they are also vulnerable to high temperatures, right? As regards a nuclear fallout, yeah, that would probably be okay. But as long as the temperature doesn't, so it's a temperature
at the
thing.
site of the explosion,
yeah, okay.
You're fine.
They're just made for apocalypses. They're absolutely fine.
Just as long as the apocalypse doesn't involve pipettes from space.
Yeah. I mean, that's their one weakness. That's their only weakness.
Their kryptonite.
Yeah. Being pipetted.
It's just me. It's just me.
He's the only person who's managed to kill a tardigrade in all this time.
They're 500 million years old.
I know. I mean, it feels like each of them individually is 500 million years old. And they've just been sitting or waiting, and then you pick one of them up and then crushed it with a piece of, chemistry equipment from a school lab.
Yeah.
What an end.
It's an astonishing end.
We did answer the question, though.
We very much did. I mean, we don't know if we can learn from them, but tantalisingly, that prospect was put before us. But they themselves remain, I'll give you invincible. On the ground that we've only had pipettes for the last 200.
A blink of the eye.
Honestly, geologically, to a tardigrade, no time at all since the pipettes arrived. Their natural predator arrived. So actually, yeah, up until that point, up until the making of fine glass tubing, they ruled supreme.
It certainly did. Yeah. Well, thank you so much to our guests, Nadia Mobek and James Fleming. I think they've got a shout at being the superheroes of the microscopic world.
Oh yeah, I now feel they're like the Eternals, some sort of creature that predates us, has been there the entire time. That's
scorching.
Yeah, and when time ends, it'll be a tardigrade who's there to just hand over the scrolls. This too shall pass. I have seen everything.
Scrolls? These predate trees, mate.
Oh yeah, true. Yeah, well they've got some form of writing it all down. Like otherwise, how would they remember it all? Or they just very quickly went, I can't be bothered. Just curl into a ball. Right. I mean, who hasn't wanted to go, I'm just going to curl into a ball and expel all the fluid in my body and just call me in 10 years. It's grand. I'm going to sit this one out.
Yeah.
But look, can we dedicate it to the one tardigrade on the moon?
I think we should dedicate it to the one tardigrade that lost its life for our episode.
Oh my God, absolutely. The only tardigrade that's ever died. Apart from the one they put into a gun and fired at a wall. I wonder if they survived. I know how we'll test it. Let's fire them from a gun at a wall and see what we pick up.
But are we sure that they definitely died, though, or were they just pretending to be dead? Because it sounds like they're pretty good at that.
Yeah, absolutely. How would you know? How would you know? You'd be prodding them for ages. There's nothing coming off. Got some water for you. I've got some water. Go to your favourite water. Turn this into an ocean. And there's nothing coming back off.
Nothing.
That's what
I do really like the idea, though, if you are 600 million years old, just everything feels very small to you, doesn't it?
They don't start saying, they're not calling things Riz and using slang, and Bay went right past them. All these things like whatever. They don't care about trends. You think the Taylor Swift versus the Beatles matters to a tardigrade?
Absolutely not. All the length of your socks for a millennial or Gen Z, no one cares. No tardigrade cares.
In many ways, an example to us. Like these things have come and gone. They'd be there going, none of these trends mean anything to me. For I am tardigrade, and I will endure. Whoa, where you come with that pipette? Subscribe to Curious Cases on BBC Sounds and make sure you've got push notifications turned on, and we'll let you know as soon as new episodes are available.
Nature Bang.
Hello.
Hello.
And welcome to Nature Bang.
I'm Becky Ripley.
I'm Emily Knight.
And in this series from BBC Radio 4, we look to the natural world to answer some of life's big questions.
Like, how can a brainless slime mould help us solve complex mapping problems?
And what can an octopus teach us about the relationship between mind and body?
It really stretches your understanding of consciousness.
With the help of evolutionary biologists.
I'm actually always very comfortable comparing us to other species.
Philosophers.
You never really know what it could be like to be another creature.
And spongeologists. Is that your job title? Are you a spongeologist?
Well, I am in certain spheres.
It's science meets storytelling.
With a philosophical twist.
It really gets to the heart of free will and what it means to be you.
So if you want to find out more about yourself,
via cockatoos that dance, frogs that freeze, and single-cell amoebas that design border policies,
subscribe to Nature Bang from BBC Radio 4, available on BBC Sounds.
Bang!
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
This BBC podcast is supported by ads outside the UK.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
BBC Sounds. Music, radio, podcasts.
I'm Hannah Fry.
And I'm Dara O'Brien.
And this is Curious Cases.
The show where we take your quirkiest questions,
your crunchiest conundrums,
and then we solve them.
With the power of science.
I mean, do we always solve them?
I mean, the hit rate's pretty low.
But it is with science.
It is with science.
There are words, Hannah, in science that sometimes mean something wonderful, sometimes mean something terrible. And there are shows I'd like to do about those words sometimes, but not about the other meaning of the words.
What's the word today?
Discharge.
Okay.
Yeah.
I think this is the only context in which a conversation about discharge that lasts for half an hour will be enjoyable for everybody.
Yeah. I mean, I can think of a load of really that are both inappropriate or unpleasant or just, repugnant.
Certainly unexpected on a Saturday morning on Radio 4.
Not the time to listen to conversations about discharge.
But this one...
Wow, this is a really good one.
This type of
this is the rug we're pulling under people here, because you're going, really? Really? Discharge?
Uh-huh.
We're going to do a whole thing about this? Like, yeah.
Shall I read you out the question that got sent to curiouscases@bbc.co.uk?
Please do.
A few of them on the same topic. Zoe from Toronto asked, how does lightning work and are there different types? Lightning, see? Hey?
That's the only type of discharge you want to talk about.
It's always better when someone explains it, isn't it?
Yeah.
We also had a question in from Simon Thompson and Amal Sharon. Why does lightning change direction? Another one, what is the probability of being hit by lightning? And one that I particularly like, can you capture the energy from lightning strikes and use it to meet the world's energy needs? That's from David Wood and Noah Willis and his friend Joe.
All of which sounds a fantastic thing. I will just say as a proviso that if any part of your body at the moment is in any way discoloured or misshapen or is discharging lightning, that's bad. We have been joined in the studio by two people who I think it's fair to say love lightning. But then again, who does not? Professor Karen Applin studies space weather at the University of Bristol.
And Dr. Daniel Mitchard is a particle physicist from Cardiff University's Lightning Lab. Dan, sounds like my kind of lab. What exactly do you do there apart from make lightning?
Well, we do a lot of investigations into how lightning interact and different types of lightning phenomena. A lot of our work has been on making sure aircraft are safe, and we're kind of moving into looking at how lightning interacts with the environment and things like climate change and things like that.
But mostly zapping stuff.
Mostly blowing things up.
Amazing.
Yes.
Amazing. All right, let's get some basics in first then. So if we start with the type of lightning that you can see out of a window, sort of below a cloud, what is it and why does it happen?
So the lightning that you see out and about when you're looking at thunderstorms and things like that is build-up of charge, usually up in the clouds or in storm cells, and all that's happening is that charge is just trying to ground itself. And so the charge will become bigger and bigger and bigger, and it will just overcome the insulation of the air, and it will just connect to ground and try and equalise that charge out.
So in terms of what you're actually seeing then, is it like a rush of electrons?
Yeah, it's a rush of electrons and charged particles, and they're going, so there's so much energy there that they're kind of exploding the air, and you see all that light and you hear that explosion as thunder.
And that exploding the air, the light that you're actually seeing is what, the gas being ionised?
Yeah, it's nitrogen, oxygen, argon in the air just being kind of torn apart, and all that light is being thrown out, and then it all kind of recombines again afterwards.
Torn into a plasma?
It is torn into a plasma, yes. It's a very hot plasma.
Wait, how hot?
It's about 30,000 degrees Celsius, about 5 times hotter than the surface of the sun.
Whoa. OK, there's potentially a lot of energy there to harness.
There is a lot of energy, but it's over a very short space of time. So a lightning arc is about 100 microseconds. So it's very, very short. And it is in gigawatts. So it is a lot of energy for a single lightning arc. But compared to the amount of energy we use every day, it's not that much, really.
Thus far, what I'm hearing is that Back to the Future was based on science fact.
Yeah, it was entirely based on science fact. I don't think anyone's quite replicated yet time travel, but you know, we can do that in the lab if you want to have a go.
Look, you said the word gigawatt and I was all on board. OK, which direction is the lightning going?
You kind of imagine that the lightning is coming down from the sky and striking something, but it actually connects maybe about 100 metres or so above the ground level, and you can actually get positive and negative lightning, which is different flows of charge in different directions.
The image I have in my head is when you rub something with it, like whether you rub the plastic rod with the sheet and you charge it statically. A balloon on your hair is a perfect example. So is a cloud essentially going through that kind of interaction that you're building up?
Yeah, so it's in the cloud you need to have a mixture of different types of water. So you have ice and water and a kind of special soft hail that's called graupel. And then because the cloud is turbulent, all the materials are mixing and wafting upwards, then they collide and you get transfer of charge from, I think it's ice to graupel, or graupel to ice. And basically, because the graupel's kind of hail, it sort of falls down and the ice is lighter, so it wafts up, so you get a separation, and that's what builds up the charge.
There is another theory that it's cosmic rays, which is kind of a minor theory as to how cosmic radiation, when you get cosmic ray showers, So as various radiation is passing through the Earth, and it will break down into lots of different particles as it passes through the atmosphere. And I suppose you could call it a minor theory, or maybe an additional mechanism might be that these particles, as they're passing through clouds, are charging the clouds or creating pockets of charge, and that will initiate the lightning. So there's different theories, like certainly the cloud charge theory is the prominent one, but there may be other mechanisms involved, and there may be other things going on.
I think they work together. So like the cosmic, you have to have your pre-charged thundercloud.
Yeah.
A cosmic ray on its own can't make a thunderstorm.
No.
But you have your thundercloud all like ready to go, and then your cosmic ray can come in and might trigger it.
I don't know about you, but next time there's a thunderstorm, I'm going to say, oh, cosmic rays are discharging
Here
again.
we go. That'll be space again.
Why do you end up getting the different shapes then?
So yeah, really below clouds, you either get cloud to ground, which is that typical lightning strike you see that forks out, and it will
like
kind
a river
of connect.
delta. That's that shape of different.
Yeah, and it will connect, and you kind of see that flicker and that kind of image in your eye of the typical fork structure. But you can also get cloud to cloud lightning, which is where the lightning is just, rather than going to ground, it's trying to equalise itself with another pocket of charge in the cloud that might be closer. So the lightning is travelling sideways in a way. So that kind of also forks, but you might not see it because it's in the cloud. So you can get sheet lightning where you just get these flashes that you don't really resolve very well. It can also go in different directions.
Okay, the fork. Why does it fork?
It's just trying to find a connection to ground. And so clouds, they're several kilometres up in the sky. And if you're that far away from something that you want to connect with, it's going to spread itself out.
Why doesn't it just go straight down?
Well, it's travelling through different pockets of air. So some air might be more or less conductive, and you'll get this process called step leaders, where it'll kind of accelerate through one pocket of air, and then it kind of meets a bit of resistance, and then it'll accelerate again in a different direction.
How much lightning is there, though? I mean, if you watched us from space, would there always be lightning going on somewhere?
Yeah, there pretty much is always lightning going on somewhere in the world. I think there's around 3 million strikes a day on Earth, so it is a lot. And there are live lightning monitors which you can watch.
Lightning watch.
Yes, a bit like Spring Watch, but maybe a bit more exciting.
That's just right. It's not called Lightning Watch. What is it actually called?
There's a couple of websites. One is lightningmaps.org.
I'm going on it.
And the other one is Blitzortung.
Real-time lightning maps.
It makes noises, actually.
Oh, hello.
It makes the
Turn it
noises.
on and it goes to...
Yeah.
Absolutely.
It'll also show you the spread of thunder.
Yeah.
So you can kind of figure out if you watch it, you can see how the thunder spreads out.
There's so many more than I thought. Look
wow.
how many there are. There's barely a moment when there isn't some sort of circle on this map. It's extraordinary. Are there some places that are more prone to lightning than others?
The closer you are to the equator, the more lightning you get. And that's really due to the type of weather systems they have that can create storms.
Does that mean that, there are people living in Norway, northern Norway, who've never seen lightning in their lives?
Yeah, the further north you go, the less lightning there is.
They've got the northern lights.
Yeah,
Come
I mean,
on,
really,
they can't complain.
Give it and take it away. You get one show in the sky, or not, but not both.
No, and at the poles, it's almost unknown.
Imagine if you were from northern Norway,
yes,
and travelled down and saw lightning for the first time. You would be convinced that it was the gods having
yeah, absolutely. I mean, the fact that they literally have a god of lightning, who's quite famous. There's been a few films recently, and yet they have never. I'm just thinking of, if penguins and polar bears ever met, it's probably the one thing they could chat about how they've never seen lightning. It's the one thing. They were on a cruise, an equatorial cruise, going, well, I'm really come here because I want to see the lightning, because I've never seen that at home. They're quite sweet.
Okay, looking at that map, though, there is much more lightning than I expected. Does that mean maybe there's a higher chance of being hit by it than perhaps we realise?
Somewhere around 24,000 people a year get killed by lightning, but in the UK, your chance of being struck is very low.
That is more than I thought. But one of our listeners, Zoe in Toronto, she wanted to know what actually happens when you get struck by lightning. So have a listen to this.
This particular trip was going to be 3 days on a reservoir in Vermont, and we were heading across the lake to a remote campsite that you couldn't access anyway other than by boat. And we knew that there was going to be bad weather. The storm came in really, really fast. So it was pouring rain, and it's so loud you can feel it, So my husband said, maybe you should check on our son, Zach. So I walked right over to his hammock and I bent down under the rainfly. And so I touched him on the shoulder with my left hand. And I said, Zach, we're going to be okay. Like, we're under the tree cover. We're not out on the open water. We're not near anything really tall. We're not near anything metal. We're going to be okay. And as soon as I said that, that's when the lightning struck somewhere. I mean, I think it must have been a ground strike. I did not get hit directly, or I would not be here telling you this story. What I remember mostly is just explosive pain in my right arm. It was like darts were trying unsuccessfully to shoot out of my skin, is the only way that I can think of to describe it. I mean, my son said he did hear me scream, and I remember hearing myself scream, but it was like this out-of-body experience. And when it was over, I realized that I was probably 5 or 6 feet at least from where I had been. Driving home, I think, was when really it hit all of us like, wow, I can't believe we're all still here.
So that was lightning survivor Kerry Evans there. And actually everybody was completely fine. They all survived it. But I thought it was interesting in that how they were talking about being in hammocks and sort of staying off the ground. Does that help to protect you?
Not really, because if it's made it all the way from the cloud to the hammock, it's going to kind of continue on through. So if you're a metre or so above the ground, I mean, it's already travelled several kilometres. I think it's also a common misconception about people who think that if they wear wellies, that might help, but it doesn't really, because lightning that powerful and that energetic can move and jump around, and it can skip those gaps to connect. It's probably better to be in what they call a Faraday cage, which is to be surrounded by something conductive. That would work.
Like in a car?
Yeah, like in a car or some types of buildings and things. Whereas if you're just putting on some kind of rubber-soled shoe, that's not really enough, because the lightning could theoretically just kind of strike your head and then jump out of your hip to ground, skipping the shoe entirely. So it doesn't really.
Okay, so far we've got get in a car to say stay. And is there any other tips you can give us? Because you're not inspiring me with hope right now.
I think the best thing to do is just
never
stay
leave
indoors,
the house.
or stay in a car, or just be in shelter somewhere. If you can't find shelter, you should just really be as low as you can, and you shouldn't be standing up. You should be
taking selfies.
Not taking selfies, or not holding anything
holding
like
a phone in your hand.
As high as possible, with a good angle.
Yeah.
We've been talking mainly about the kind of lightning we see below cloud, but you mentioned there are other types of lightning above the clouds, and they are much more varied, much more interesting in some ways.
Yeah, there's a whole family of very interestingly named phenomena that are generally too quick for the human eye to see, and they reach up to the edge of space. And you can look these up online, because some of them are quite fantastical and like nothing you've ever seen before. So from the clouds up, you get things called jets, and they are kind of like lightning. They're a bit more linear. They can reach up anything from 10 kilometres up to 90 kilometres, so right up to the edge of space. And there's 3 classes of those. There's blue starters, which are the small ones, blue jets, which are kind of the common ones, and then you get gigantic jets, which reach all the way up to the edge of space.
What is that, the official name?
They are the
jets.
official names. Oh, you wait till there's a point in this where it happens in particle physics, where scientists run out of names for things, and so they kind of start thinking of other names. If you go above 50-kilometre altitude, you will see these big, giant red structures called sprites, and they are often described as jellyfish-like or carrot-like. And they are huge. They can be about 40 kilometres across, and they can be about 40 kilometres, 50 kilometres tall. Sprites will have these tendrils that hang down, and some of those tendrils are called trolls. Probably one of the most recently discovered things that kind of sit on top of sprites are ghosts, which are green in colour, but they're incredibly hard to see, a bit like well, it wouldn't be their real life counterpart, would it? And then you get elves, and elves are giant halos that kind of sit up to about 100 kilometres, and they can spread out to about 400 kilometres. They're like giant discs. There's a whole range of other things. There's
pixies.
There are pixies, and there are gnomes.
Gnomes?
Yes.
Jesus, lads, you went heavy on the whimsy on this one, yeah, you know. We've drifted away from the science question.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.
Sharply. Dan, you brought something that will create lightning right in the studio for us.
Yeah, so we've brought a Tesla coil here in the studio, and it's not lightning as such, but it's a very good way of visualizing how a lightning arc behaves. It's particularly good to demonstrate how lightning doesn't need to connect to ground. And here in the studio, there isn't anything to ground itself, so it will just dissipate into the air and not connect to anything.
Well, we're all here.
You can try and ground it yourself by standing next to it.
What's its range of influence, this particular machine?
The arcing will probably reach out to about 20 to 30 centimetres, and we've got a 2-metre cordon around it. Tesla coils are high frequency, high voltage. They're a little bit different to lightning, which is high current, high voltage. If you use the waterfall analogy, the voltage is the height of the waterfall.
Yeah.
And the current is the amount of water coming over it, because you can imagine that a waterfall that just has little drips coming off it, if you're standing at the bottom, that's not going to feel like much.
You've got a really high waterfall with hardly any water going over it. Not that big of a deal. But you go to the Niagara, high waterfall, absolute shed load of water going over the edge of it, extraordinarily full of energy, like loads and loads of energy going.
Lightning is both high voltage and high current.
The voltage is the thing that basically insists that it happens.
In lightning terms, it allows it to travel. You need a very high voltage to travel a longer distance. So in lightning, you need to have it be in the gigavolts to kind of create that channel across kilometres of air.
That voltage occurs because of the difference in charge between the clouds and the ground.
Yeah, and it's built up through these processes.
So it sort of is a waterfall then, but just of electrons.
Yeah, so the Tesla coil is very small current, very minimal.
A weeny skinny waterfall.
Microamps, but it's very high voltage. So you still create these arcs that are reaching out, but there's very little energy behind them, as it were.
We've dimmed the lighting in the studio, making it a much more kind of sedate, kind of moody affair. And we should see an arc of lightning.
You'll see a nice blue arc kind of spreading, forking out into the air.
So I guess we should describe what Tesla coils look like.
Yeah.
You've got a lot of copper wound around a central cylinder.
Yes.
And then a sort of donut sitting on top. What's the purpose of the donut?
So lightning likes to come out of pointy things. So the donut is really there just to make sure that we can direct the lightning only to the needle that we have on top of it, rather than it going out in all directions.
So when you charge it up, it's the end of the needle we should be looking out for.
Yeah.
Can I ever go press the button? Can I press the button?
Obviously.
Yeah. Right. Fixed mode. And is that the one that brings the frequency up? I'm cranking up the amplitude. Then I press button middle. Frequency 1 hertz. I'm making that happen. Real sense of elemental power there. Real sense of I am master of the universe in that moment.
But I mean, you sort of are in a way, because you're taking something that's like exists on a global scale and you're just creating it in a small studio in the BBC. Karen, is it only us, or do other planets have lightning as well?
Yes, so there is lightning on other planets. Mars, lightning is basically thought to be there, but no one's ever seen it. And that's because Mars is very dusty and the dust blows around and kind of rubs together. And there are dust devils on Mars, and we know that dust devils on Earth get electrically charged, they have voltage in them. So if you were to transport that dust devil to Mars and sit it there, it might well have lightning in it, because it's actually easier to make lightning in the Mars atmosphere because it's thinner. So we do expect lightning to be there, but yes, it's never been detected. So
where have we detected? Have we detected it on Venus?
Venus is a bit controversial. Some people think they have detected it. Other people haven't detected it when they think they should have done. Where we have seen it, and nobody argues, is Jupiter. Loads of lightning on Jupiter. Pretty much all the spacecraft that have been to Jupiter have seen lightning there.
OK, if we are at the point where we're considering exploring other planets, is this something that we have to be a bit concerned about lightning strikes on other planets?
Yes, it is. Yes. So there's very much, we're going to be sending people to Mars in the next, I don't know, very optimistically, maybe 20 years, more realistically, 50 to 100 years. And it's a hazard, just as it's a hazard on Earth. So obviously, if you have astronauts and they're walking around, there's a risk to them. If there's a lightning storm, probably you would just make sure they didn't go out of the spacecraft at the time there was a dust storm or something if they're on Mars. I think probably more like realistic hazards are things like disturbances to electrical systems, because lightning generates a lot of noise, as we've heard, and electrical noise, and that could, sparks and things aren't good for electronics generally, so you might have problems with your spacecraft systems. And you don't have to have lightning for there to be a problem, because if it's like lots of charged dust blowing around, then it can stick to solar panels, and that causes a problem for your power generation. So it is definitely something people need to be aware of, particularly as Mars is the place we're going to go, and there is electricity in the Martian atmosphere.
I'm just thinking back to how you were describing that lightning occurs, which is the movement of different types of water within these clouds. On other planets, is it the same mechanisms that's causing the lightning? Because water on other planets is kind of a key question, isn't it?
Yes, it is a big question. It's a mixture of ways that lightning's generated on other planets. On Jupiter and Saturn, where the lightning's been seen, we believe that it is mainly from water clouds, and that is because it's quite deep in the atmosphere, and we can sort of work out what height roughly those flashes come from, and then that corresponds to sort of a temperature at which you have water and ice. So that suggests the same mechanism as we have on Earth. But on Mars, it's actually the same mechanism as volcanic lightning, and that is due to dust and ash being spewed out of the volcano and rubbing.
I mean, in the good old days, when the Earth was mainly volcanoes, there was a lot of lightning, wasn't there? In the early days of Earth's formation.
I don't know if we know that there was more or less. We do know it's been there the whole time Earth's been around, and that's because you can find fossilised lightning strikes called fulgurites in rocks. So I don't know if there was more or less, and everything's changed as well. The atmosphere was different then, but there certainly has been lightning the whole time.
Was it important for life, possibly?
Potentially. There's a very famous experiment from the 1950s where scientists Miller and Urey got a kind of tank, and they put some chemicals in it that they believe to be representative of pre-life Earth, and then they
like a sort of swamp that existed.
Yes, exactly, a primeval swamp or something, and then they zapped it with a spark to represent lightning. And I think after quite a long time, after about a year, they found that there were some amino acids had been formed inside.
They caused life.
Well, amino acids
sure.
aren't life.
I mean, blah, 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 blah. They're getting there. They're closer. They're closer. Is that a theory, that actually life started because of a lightning strike?
It's one theory.
I love it.
It's great, isn't it? Yeah. I mean, it's also much more fun than the geothermal vaults, down the garden there. Look at that thing. Okay, fine. That's all they do, whatever. Yeah. But
yeah,
it's fantastic.
It is. I really like that.
Yeah.
This sounds like we're straying very far into science fiction here. But is this a legitimate theory that people have?
It is a legitimate theory, and I think for Earth, very much. I think on other planets, probably not the same, because you don't have the same mix of stuff that you had on Earth. But certainly lightning has things it does for chemistry. It's a big burst of energy that you're putting into a gas, the atmosphere, that you wouldn't otherwise get.
We have established there are really lots of different types of lightning, and the lightning of the planets could be the key to discovering whether they be habitable or not, or whether life has existed there maybe. But let's get back to Earth, because one of the questions I wanted to know about whether we can use it. Dan, can we capture lightning? How much power is there?
We would measure this in current. So if you think that your domestic supply is 3 to 5 amps, say, an average lightning strike is about 30,000 amps.
So that's a lot of power for a brief period of time.
It's about 100 microseconds, so yeah, it's a fraction of a second.
But there's something there that we could grab?
I think it's always been a dream of a lot of people to try and capture, to bottle lightning. People have tried, and it's kind of in the imagination of human society to do this, but there are big issues, and I think the two main issues are, one, lightning is inherently random, so it's really hard to predict where it will strike. Yeah. And then the second one is that this energy is delivered so quickly that there's no technology really that can store it that quickly. It will just blow things apart. And I guess the other point of that is that for our needs as humans, even though it is very energetic for that brief amount of time, one single strike is not going to give you sufficient energy for what we use it for. You'd have to capture a huge amount of lightning strikes to kind of make it meaningful.
270 years ago, Benjamin Franklin went out with a key on a kite. So this is something we've been trying to do for a while now.
We move very slowly as lightning scientists.
I mean, it should be pointed out that Franklin didn't go out and get hit by lightning, although he could have been, but he did just dangle onto a rain, like a dangle kite into a
he flew a kite in a thunderstorm to try and attract lightning to a wire with a key on it that was hanging on it, in an attempt to capture and study lightning. The kite was on a insulated bit of string, so he was quite far from the strike.
And was he wearing wellies?
Well, I wasn't there at the time, but maybe.
But that, you couldn't just do like a slightly better wire than Franklin had 270 years ago. You could do essentially the same technology. You could lift a drone up there or something and essentially drain the cloud of charge is what I'm asking. Why can't we do that?
It's a very difficult thing to do, and maybe we don't fully understand the processes and how these things are created, but it is a long way up, and there's a lot of myths about lightning as well. It won't necessarily go for the highest point, and it won't necessarily go for the conductive thing. It kind of just will do what you don't think it should do, and kind of is still very unpredictable.
So maybe we can't capture it, but we can certainly learn, and that's what you're doing, about its effects on the atmosphere, because it creates greenhouse gases, doesn't it?
Lightning produces nitrogen oxide, nitrogen dioxide, ozone. We know that nitrogen oxide, nitrogen dioxide, or NOx, as it's quite commonly known, is a greenhouse gas, and through some other chemical processes can contribute towards global warming. And there are estimates for every degree of global warming, lightning on Earth will increase by about between 12 and 35%. It depends where you are, and it depends where in the world it is, and quite how this will be, how this is impacted and how the energy of lightning might change. But really, for every degree of global warming, you're getting more lightning. More lightning is putting more greenhouse gas emissions into the atmosphere, and I think the current estimates are that lightning contributes something like 15% of all of the world's NOx emissions. It can kind of create a bit of a runaway effect. So as the world warms up, the predictions are that we will see more lightning, and it might be more energetic, and it might be more frequent, and it might occur in places that it hasn't occurred in before. There's some studies a while ago that say that people are starting to see it in the poles now when it wasn't there before, for example.
So those polar bears.
Yeah, the polar bears finally get to see it. I mean, that's a bittersweet kind of finale to that, like whatever. It's not a great sign that it's there, but at least the polar bears, in their last action, get to see the lightning. Right.
While sitting on a slowly decreasing ice block. Okay, well, on that probably quite depressing note, I think it's time for us to thank both of our guests, Dan Mitchard and Karen Ablin. Thank you. Here's what I'm hearing. He did say that no one has managed to capture lightning yet, but he didn't say it's impossible, did he?
He did not.
It sounded like a big fat not yet to me.
Yeah, it did, absolutely. And maybe go back to first principles of going out in a rainstorm with a key on a kite.
Hey, what a way to go.
Yeah. I mean, it really would be. I mean, it would be a Look, how did it happen?
Look, lightning giveth life, and it taketh life away.
It certainly did. Yes. But anyway, look, there we go. Discharges. Discharges are fun.
You enjoyed that, didn't you?
I did. Subscribe to Curious Cases on BBC Sounds and make sure you've got push notifications turned on, and we'll let you know as soon as new episodes are available.
From BBC Radio 4, Britain's biggest paranormal podcast is going on a road trip.
I thought in that moment, oh my God, we've summoned something from this board.
This is Uncanny USA.
He says, somebody's in the house, and I screamed.
Listen to Uncanny USA on BBC Sounds or wherever you get your podcasts. If you dare.
Hello, it's Ray Winstone. I'm here to tell you about my podcast on BBC Radio 4, History's Toughest Heroes. I've got stories about the pioneers, the rebels, the outcasts who define tough.
And that was the first time that anybody ever ran a car up that fast with no tires on. It almost feels like your eyeballs are going to come out of your head.
Tough enough for you? Subscribe to History's Toughest Heroes wherever you get your podcast.